first talk is Mary Barth. It's Thunderstorms and Atmospheric Chemistry.
Okay, so the children of Charles Barth were asked, I guess the organizing committee was interested in what the children of Charles Barth do with their careers. And so they asked us to present some work that we've been doing. And I guess I'm first up. I'm the youngest of the 4 children, and this is probably one of the first times I get to go first. My brother Jack said, hey, I got it easy because I'm talking about thunderstorms and I can show lots of pretty pictures. And so here are my pretty pictures of thunderstorms on this first slide. Hopefully there'll be a few more in this presentation. When I went off to graduate school, I started to learn about clouds and chemistry under the auspices of acid rain. And a lot of that had to do with aqueous phase chemistry, what chemistry was going on inside the clouds. But then once I was done with that, I learned about thunderstorms and found out how fascinating they were. They're complex storms, and there's a lot of effects, processes going on affecting the chemistry. And so you're going to see this picture a lot during my presentation on how thunderstorms can affect chemistry. And one of the ways this happens is, one of the major ways is that you get transport from near the surface. All these pollutants, all these surface emitted species get transported up to the upper troposphere, 10, 12 kilometers above the ground. But there are other things going on. I mentioned the aqueous chemistry. There's this deposition, the scavenging removal of soluble trace gases down to the ground inside the rain. Another major process, very interesting, is this production of nitrogen oxides from lightning. And so that's another big factor from thunderstorms. And so I'm going to focus a little bit more, instead of saying chemistry in general, but talk about ozone. We've heard about ozone. We know the ozone is really important to us in the stratosphere, where it blocks UV radiation and protects us from that harmful radiation. But we also know in the upper troposphere that ozone acts as a greenhouse gas. And so that's a critical thing to learn about. As you work your way down in the troposphere towards the ground, we haven't actually seen many plots that go all the way to level 0. And so I thought I'd bring it down to the ground. But as you get there, ozone is a major oxidant in the atmosphere and does a lot in transforming pollutants into less harmful conditions. But at the surface, ozone is a major pollutant. It affects our human health, it aggravates us, the respiratory system, and it also affects our ecosystems, including agriculture. So what's interesting about thunderstorms is that it connects things from the surface, where we have these pollutants down low, and brings it up to the upper troposphere, to a region where ozone acts as a greenhouse gas, and that's what I will talk about more today. Okay, so what I wanted to emphasize are these major processes. We're bringing these volatile organic compounds, CO, methane. These are some of the things you hear about in your emission controls of your cars. Those get transported up. You combine that with the nitrogen oxide that's formed from the lightning, and you mix those things together. You make these Hox radicals. You heard about that earlier, and NOx radicals. Add the two together with sunlight, and you can make ozone. And so that's what we're trying to understand. So how do you figure this out? How do you go measure this and understand what's going on? And what we've done in the past is we take airplanes and we fly in this area where air is going into the storm and measure the composition of what's going into the storm. We put airplanes up high in the Anvil region and measure what's coming out of the storms. And then we also characterize these storms using radars and lightning mapping arrays. We did this 3 years ago with the Deep Convective Clouds and Chemistry Field campaign back in May and June 2012, where we based our operations in Salina, Kansas, but we sampled thunderstorms in northeast Colorado, West Texas to Oklahoma, and northern Alabama. I'm going to give you an idea of how we operated. This is a severe convective storm in Oklahoma. It was so severe it made hail the size of a fist, as you see in the bottom right there. But this is, we knew it was going to be a strong convection day. We sent our airplanes out, and you can see that our two airplanes are out starting to sample the composition, and there's no convection out there. But just a hint of it. And as soon as we saw the convection show up, we sent one of our airplanes down low to measure what was in the region closest to the surface. We sent the other aircraft up high to measure what was in the outflow region. And you can see as we march along that the storm got very severe, but we got some really good measurements from this particular storm. So next, I'm going to shift to talk about some of our science highlights from this field program. First one I want to talk about is at the top of the storm. There's actually, at this fine scale of these thunderstorms, a lot of interaction going on between the troposphere and the stratosphere. And one of those, one way is moving things from the troposphere into the stratosphere. On the left, you see a figure of weather radar data, so what you see on the weather channel, but now you're looking at a vertical cross-section. And you can see that that storm is going up to 15, 16, even 17 kilometers, and it's going 3-4 kilometers up above the tropopause here, marked with this black line. This is actually a case where we had a double tropopause situation, but it's moving water vapor into the lower stratosphere, and that's very important for the stratospheric chemistry and radiation. On the right is a picture from LIDAR of ozone. And so you can see the high ozone concentrations in the stratosphere up here. In black, shown here, is the edge of a cloud anvil, a thunderstorm anvil. This is actually a mesoscale convective system, one of the largest storms that we have in the central US. And what we see here going on is the stratospheric ozone is wrapping around that anvil, coming into the upper troposphere. And so that can actually be a source of ozone into the upper troposphere. So there are very interesting pictures that we got. I'm going to move to the lightning aspect and how it produces nitrogen oxides. One of the things that we noticed from our lightning mapping arrays is that the lightning flash rate is inversely proportional to the extent of the lightning flash. And so you can see in this bottom right picture that you don't just have a straight line of lightning going from cloud to surface, but you have all these branches. And so we can estimate how big that lightning flash is, and we call that a flash extent, and that's shown in the red here. And then you can compare that to the flash rate, which these lightning mapping arrays do. Let's count the number of flashes. And you can see from these two lines that there seems to be an inverse correlation. And that's important because we think the production of nitrogen oxides is correlated with that lightning flash extent. And this is a plot that we just recently made for a paper that's soon to be submitted, where except for this one storm, we see a fairly good correlation between the amount of nitrogen oxide produced from these lightning flashes with the lightning flash extent. We've also been looking at the convective transport of these soluble trace gases. I mentioned them before in terms of wet deposition. We've been estimating the scavenging efficiency from a number of storms for a few key ozone precursor species. There's hydrogen peroxides, formaldehyde, and methyl hydrogen peroxide. And so basically the way to think about it is that we have a couple of parts per billion of these species near the surface of the Earth. They're getting transported, but only a few hundred parts per trillion are making it up into the upper troposphere. And so knowing how much we can count on getting up there feeds into how much HOX will be produced, and therefore contributing to the production of ozone. And so that's where I want to move to next, is figuring out how much ozone is getting produced from these thunderstorms. And that's something I can show here. So what we're seeing is that there's about 10 to 15 parts per billion of ozone being produced over the next day. And that's in comparison to having 50 parts per billion of ozone in the background. This is a really nice example. We went out to sample a thunderstorm, actually a mesoscale convective system again. These storms are strongest at nighttime, and then when day breaks, they start dissipating. And so with that knowledge, we took an airplane and we went out early in the morning, and this is at about 7 a.m., and we started flying in the anvil region of the storm and started measuring what the composition was like. And as we expected, we had really low ozone values of about, it looks like about 70 parts per billion. No, it's probably 50 parts per billion. This is really small. And so the plane, we tried to keep in that same air mass throughout the day. And so we were flying it back and forth along this air path. And you can see that the ozone level stayed low for a while. And then, boom, the sunlight shone up, and we started getting a lot more ozone. Our second plane came out and took over and flew the afternoon apart, and you can see ozone continued to increase. And we definitely see increases of about 15, maybe even more, parts per billion of ozone from this one particular case. So a lot of people have been showing pictures of my dad, and so I thought I'd do that as well. I had to look hard to find one where there were some clouds or thunderstorms in the background, but I did find one in front of Grand Lake, and I wanted to end my talk throwing up my points, but having you enjoy these pictures of thunderstorms and my father. Thank you.
Is Dad interested that you got into nitric oxide?
He did, you know, I've been doing the lightning nitric oxide stuff a little bit more as a fringe thing. I don't fully dive into that.
So you must have brought in the word photoelectrons at some point. I mean, it's similar,
Yeah.
right?
Yeah, there's some similarities, but it's measured differently because we have in situ measurements from the aircraft. It's not an exact overlap, but
No.
but he is definitely interested in what we did learn. Yes.
That's great. Anything else? Thank you.
Yes.